Welcome. This video is going to take a look at how to use stoichiometry. And stoichiometry is a funny word, but it's the study of the quantitative relationships between amounts of reactants used and products formed by a chemical reaction. So what does that mean in English? It means if you know what you're starting with in a reaction, you should be able to predict what you'll get. Or if you know how much product you want to make, you should be able to predict how much of the reactants you'll need. And this is done all the time in industry. And in fact, you probably, whatever job you work in, you will do some similar conversions. And it's based on the concept of the conservation of mass. Atoms can't be created or destroyed during a reaction. So the idea with stoichiometry is that you have to first start with a balanced chemical equation, because that's going to tell you your ratios or amounts. So a chemical equation allows us to calculate the mass of reactants or products because it's telling us, first of all, the elements or ingredients we have, and second, the amount or number or ratio of those ingredients that we need. So for example, if you have a recipe and you need 2 eggs, a cup of sugar, a stick of butter, whatever, the eggs, the butter, the sugar, that's your ingredients. But in a chemical equation, we see those ingredients as chemical formulas. So things like H2O or CaCO3, that's telling us our ingredients. And then the amount or number or ratio is being given to us in front of, when we see 2H2 plus O2 gives us 2H2O, this is our recipe here, the numbers in front. Remember, a lack of a number is telling us it's a 1. I better change that because it looks like an H now. So when we look at the 2, 1, 2 in front of these ingredients here, we can really think of those numbers as meaning 2 different things. This is telling me 2 molecules of H2 reacts with 1 molecule of O2 to form 2 molecules of H2O, but I can't even measure a molecule at a time, so I can actually think of this as moles instead of molecules. 2 moles of H2 will combine with 1 mole of O2 to form 2 moles of H2O. So here's another example to look at. Given Al plus O2 forms Al2O3, balance the above equation. So I'm going to encourage you to pause this and go ahead and balance, and I'll do the same. So if you balance this correctly, you'll need a 4 here, a 3 here, and a 2 here. So now it says, interpret the equation in terms of atoms or molecules. Well, a couple of reminders. Remember, an atom is all alone with no subscripts or no neighbors. So I know aluminum is an atom, whereas O2, even though it's still a pure element, that's considered a molecule. And then Al2O3 is technically considered a formula unit because it's a compound and it happens to be an ionic compound. And I'm not too worried if you distinguish between a molecule or a formula unit. They're representing covalent compounds and ionic compounds. But my reminders down here is an atom is all alone, no subscripts, no neighbors, whereas molecules or formulas are more than one or a few atoms bonded together. So it has a subscript or it has a neighbor. So if I interpreted this equation in terms of atoms or molecules, I would say 4 atoms of aluminum combines with 3 molecules of oxygen to produce 2 molecules of aluminum oxide. If I were to interpret this or think of this equation in terms of moles, I would think 4 moles of aluminum atoms react with 3 moles of oxygen molecules to produce 2 moles of aluminum oxide molecules, or formula units actually. And then finally, to interpret the equation in terms of mass, what I'm going to do is I'm going to look up the mass of each of these, and I'm going to see that aluminum weighs 26.98, so 4 times 26.98, plus 3 times 2 oxygen at 16 each, should equal 2 times, now I have 2 aluminum at 26.98 and 3 oxygen at 16 each. And if I actually multiply those out, those two need to equal each other. And you can see I've got 4 times each aluminum and 6 times each oxygen, so it shouldn't be a big surprise that I come up with 203.92 for each side. But again, it's just verifying that nothing is created and nothing's destroyed. So given this equation, when I interpreted this in terms of atoms or molecules, remember I balanced it with a 4, a 3, and a 2. And in terms of atoms, I would say 4 atoms of aluminum react with 3 molecules of oxygen, and you can write the names out for these compounds if you want, to produce 2 formula units of aluminum oxide. And interpreting it in terms of moles is going to be very similar, but now I'm going to say 4 moles of aluminum react with 3 moles of oxygen to produce 2 moles of aluminum oxide. And in terms of mass, I did that on the previous one, so I won't write that out again. But again, this is what you should be thinking when you look at a chemical equation. You should realize it's telling you your ratio of particles, atoms or molecules, or it's telling you molar amounts. And we more often are thinking in moles, so it's a unit to measure. The last idea to talk about with stoichiometry to start is this idea of mole ratios. It's a ratio between the number of moles for any 2 substances in a chemical equation. And why do we care? Because this is going to give us our conversion factors, okay? Just like going from particles to moles or moles to grams, you need a conversion factor. To go from one part of an equation to another part, you need a conversion factor. And we are going to use lots of mole ratios. It is the key to stoichiometric calculations. So let's take a look at an example. I've got my same equation here, and it says, what are the 6 mole ratios for this equation? Well, I could have 4 moles of aluminum, and I could compare it to 3 moles of O2. Or I could compare my 4 moles of aluminum to 2 moles of Al2O3. That would be if I wanted to find out how much aluminum I needed and I had the oxygen or the aluminum oxide. I could also be wanting to find out something about my 3 moles of oxygen compared to my aluminum. And now you notice that this converter flipped from 4/3 to 3/4. Or I could be thinking about my 3 moles of oxygen compared to my product, 2 moles of Al2O3. Molar ratios don't matter if you're comparing reactant to reactant or reactant to product or even product to product. And the last thing could be is if I was interested in the Al2O3 compared to the aluminum, or my 2 moles of product compared to the oxygen. So those are the 6 possible mole ratios. We could convert 6 different ways from this one equation. Now, realistically, you're not going to have to write all the molar ratios for something. Instead, what you're going to need to do is answer a question like my second one here. Which mole ratio would you use if you had a known amount of aluminum? So what I have is X moles of aluminum, and I want to predict the amount of aluminum oxide. So I would want to set up a molar ratio of what I want, moles of aluminum oxide, over what I have. I know my moles of aluminum. I want to know aluminum oxide. And according to my equation, that means I should put 2/4. Now that's a big difference to cut something in half, 2/4, than it is to put 4/2 and double it. So it's very important you get the molar ratio set up in the correct order. So here's an example for you to try. Write all the mole ratios to the above equation, and there should be 6 again, just like there were in the previous problem. And then tell me what ratio you should use if you have a known amount of potassium chlorate and need to predict how much potassium chloride will form. Now you notice you need to know what these names, which formulas these names match up with. And in fact, oftentimes you'll be expected to write the balanced equation to get things started. So I would suggest you pause and try this on your own, and then watch as I go through my solution. So all the mole ratios, I'm just going to do this in an order so I don't lose myself. I'm going to put KClO3 on top. I could predict how much KClO3 if I knew my moles of KCl, or I could predict how much KClO3, potassium chlorate, if I knew how much product, or how much of the other product I had, 3 moles of O2. I could predict how much KCl I would form if I knew my moles of KClO3. Now in this case, the two, this one and this one, it works out the same because they both have the same coefficient, but that's just a coincidence. Or I could predict how much KCl would be formed if I knew how much oxygen was formed. And finally, I could predict my oxygen if I knew how much KClO3 I was starting with. Or I could predict my oxygen if I knew how much KCl was being formed. Oh, but that's a 2 there, not a 3. So follow my own advice and get the numbers right. So then finally, what ratio should I use if I have a known amount of potassium chlorate? So this is what I have. So I'm just going to put X amount of KClO3, that's potassium chlorate, and I want to predict how much potassium chloride, so I need to know KCl from KClO3, so this would be 2/2.